What is cosine of I? Now that might seem like a strange question to ask because for the cosine function, don't we usually just enter in angles? So cosine of an angle is adjacent over hypotenuse. Or we could use the unit circle definition of cosine, where cosine of an angle is defined to be the x-coordinate of a certain point on the unit circle. But what about cosine of I? How can we make any kind of sense of that? Well, that's what I want to show you in this video. We're going to extend the definition of cosine beyond the real numbers to the complex numbers. And I want to show you how to do that in this video. But before we go any further, let me just cut to the chase. Cosine of I, turns out it's e plus 1 over e over 2, which as a decimal, this is approximately 1.54308 ... Now, this may seem a bit strange for several reasons. So first of all, why is the number e getting involved here? What does cosine of I have anything to do with the number e? And second of all, notice that we're getting a real number as an output. And it's not clear why should we expect cosine of I to be a real number. In fact, sine of I is not a real number. And I'll explain a bit about that at the end of the video. But cosine of I is a real number. And not only is it a real number, it's a real number that's bigger than 1. And don't we tend to think of cosine as being a bounded function, right? It's bounded between -1 and 1. Well, the complex cosine function, where we allow complex numbers as inputs, is not bounded. We can get outputs that are bigger than 1 or less than -1. Now, I should point out that we can, of course, rewrite this as e to the 1 plus e to the -1 over 2. Now, let me take off my video here. And you may or may not recognize that this is cosh of 1, hyperbolic cosine of 1. Now, if you've never seen the hyperbolic cosine function before, cosh of x, or hyperbolic cosine of x, is defined to be e to the x plus e to the -x over 2. It's really the average of e to the x and e to the -x. And so notice that cosh of 1, hyperbolic cosine of 1, would be e to the 1 plus e to the -1 over 2, which is exactly what we have here. Now, when I first encountered the hyperbolic cosine function, I think it was a calculus class, I wondered, what does this have anything to do with cosine? Right? Why is this called hyperbolic cosine? E to the x plus e to the -x over 2. Well, it turns out it's only when you get to the realm of complex numbers, when you're dealing with imaginary numbers, where you can see this connection between hyperbolic cosine and the original cosine function. So how do we define cosine of z? Okay, now we tend to use the letter z when we're talking about a complex number. So how do we define this complex cosine function? Well, we have two equivalent definitions of cosine, and I'm going to explain both of these definitions. So first of all, we have a power series definition of cosine of z. So I'll explain this in a second. But secondly, we have cosine of z is defined to be e to the iz plus e to the -iz over 2. And in terms of practicality, this second definition is actually easier to use than the first definition. But let's look at this one first. Now, if you've taken a second or third semester of calculus, you should have seen the concept of power series. And we have these power series representations of cosine of x, sine of x, and e to the x. And if you haven't seen these before, I should really say these are some beautiful formulas. In fact, I remember the first time seeing these formulas, I was just blown away. In fact, I think I was in high school when I saw these. I think I was actually looking in an Encyclopedia Britannica. Tells you how much of a nerd I was. But cosine of x can be represented by this, well, what looks kind of like an infinite degree polynomial. So cosine of x, in fact, I think you should try this if you haven't seen these before. Graph on, let's say, Desmos, graph cosine of x, and then graph the function 1 minus x squared over 2 factorial, so that quadratic function. Then graph 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Graph that. In fact, let's go ahead and do that in Desmos real quickly here. So I've graphed y equals cosine of x. Now if we graph y equals 1 minus x squared over 2 factorial, notice that the graphs kind of coincide. They sort of hug each other near x equals 0. And if we add another term, so the next term was plus x to the 4th over 4 factorial, the graphs line up even better. If we add another term, x to the 6th over 6 factorial, we get an even better approximation. So this blue graph is approximating the red graph near 0. Now you might think, well, the graphs don't coincide very well out here. The graphs definitely don't line up out here, but that's just because we haven't added enough terms. The more terms that we add, not only does the approximation start getting better and better in here, so that the graphs start looking more and more like each other, but the approximation starts working farther and farther out here. And in fact, if we add infinitely many terms, the two functions actually line up exactly. They're the same function. So I think this is truly remarkable. But to really understand this, though, you need to have had a second or third semester of calculus. So we have these power series representations not only for cosine of x, but also sine of x and e to the x. Now, to define cosine of z, what we can do is just replace each of these x's in this formula with z's. And if we do that, we get our definition here for cosine of z. And now if we want to find what's cosine of I, we just replace the z's with i's. And remember that I squared is -1, I to the fourth is 1, I to the sixth is -1. And it's going to alternate back and forth between 1 and -1. So cosine of I ends up being 1 plus 1 over 2 factorial, plus 1 over 4 factorial, plus 1 over 6 factorial, and so on. And now the question is, what is this series sum to be? Well, you can add up enough terms, you can get a decimal approximation. And this, you can see if you add enough terms, you'll see it's starting to get closer and closer to this number right here. But what does the series sum up to be exactly, rather than just this decimal approximation? How could we figure out what it sums up to be exactly? And it turns out it's cosh of 1, like I mentioned, but why is it cosh of 1? Well, remember that the power series for e to the x is this. So if we want to find the power series for e to the negative x, we just replace all the x's with negative x. If we wanted to find the power series for e to the 5x, right, we just replace all the x's with 5x. Okay, we're trying to find the power series for e to the negative x, though. We replace the x's with negative x's, and then we can simplify this down. So negative x squared, of course, is just the same thing as x squared. In fact, for any even power, the negatives are going to drop out. For the odd powers, though, the negatives can come out front. So this simplifies to be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, and so on. And the whole point of doing this, though, is so that if we were to add e to the x and e to the negative x, what would happen? Well, if we were to take this plus this and add them up, notice the x and the minus x, if we add those will go away. The x cubed over 3 factorial and minus x cubed over 3 factorial, those will add to 0. All the odd powers are going to add to 0. All the even ones just double up. So what we end up getting is 2 times 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus x to the sixth over 6 factorial, and so on. And so notice that e to the x plus e to the negative x over 2, if we divide both sides by 2, ends up being the right-hand side. But remember, e to the x plus e to the negative x over 2, that's cosh of x. So here is actually a power series representation for cosh of x. It's 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus x to the sixth over 6 factorial, and so on. And notice that cosh of 1 would be this number 1 plus 1 over 2 factorial plus 1 over 4 factorial, and so on. And that's this number here. So in other words, this is cosh of 1. Okay, so we've used our first definition of cosine of z to find out what cosine of I is. Now I mentioned that this definition doesn't always work too great in other practical situations. So if we were trying to find what's cosine of 2 plus 5i, well, the reason that I worked so nicely was because I squared, I to the fourth, I to the sixth, those simplified so nicely. But if we were trying to find like cosine of 2 plus 5i, well, we'd have to do 2 plus 5i squared, 2 plus 5i cubed, and so on, and those don't simplify so nicely. So in actually most situations, this second definition is going to work better. So where does this definition come from? Well, it turns out it comes from Euler's formula, which is this wonderful little identity that says e to the I theta equals cosine theta plus I sine theta. But where does this come from? Well, it comes from these three power series. So specifically what you do is you take the power series for e to the x and you replace all the x's in this formula with I theta. So you get e to the I theta equals 1 plus I theta quantity squared over 2 factorial, and so on. And it turns out if you do that, if you simplify the right-hand side, it's going to turn out that every other term is going to have an I in it, and every other term is going to be missing an I. It's not going to have an I. If you separate out the terms that have I's from the terms that don't have I's, what you end up getting is the power series for cosine theta plus I times the power series for sine of theta. It's really a beautiful and remarkable thing that happens. In fact, it's almost awe-inspiring, and you really should try this on your own if you've never seen it before. So e to the I theta is cosine theta plus I sine theta. Now, what if we replace the thetas in this formula with negative theta? Well, we could write the left-hand side as just e to the negative I theta equals, well, cosine of negative theta is just cosine of theta because cosine is an even function. And sine of negative theta is negative sine of theta because sine is odd. So we get minus I sine of theta. Now we tend to think of theta as being a real number, really like an angle that we're plugging into sine and cosine. But what if we replace these thetas in these formulas with z, a complex number z? Well, Euler's formula would be e to the I z equals cosine z plus I sine z. And this version of Euler's formula would say e to the negative I z equals cosine z minus I sine z. Now, what would happen if we took e to the iz and added it to e to the minus iz? So basically take this formula and add it to this formula. What happens? Well, e to the iz plus e to the minus iz, what would end up happening is we'd get cosine z plus cosine z, that's 2 cosine z. And we'd have I sine z plus a minus I sine z, that would go away, those would disappear. So notice now we have this formula. If we divide both sides by 2, we get that cosine of z is e to the iz plus e to the minus iz over 2. And that was our alternative definition of cosine of z. In fact, that's the definition we see here. And now it's actually very straightforward and simple to figure out what is cosine of I based on this. Well, it'd be e to the I times I plus e to the minus I times I over 2. And of course, I squared is negative 1, so this is e to the minus 1 plus, well, I squared is negative 1, but we have another negative, so that makes it e to the 1. And notice this is just e to the 1 plus e to the negative 1 over 2, like we said it was. And again, that's just cosh of 1. So notice we found cosine of I using both definitions here. Now, one thing I want to point out is our definition of cosine is it's e to the iz plus e to the minus iz over 2 cosh of z. So remember, cosh of x is e to the x plus e to the minus x over 2. So cosh of z, you just replace these x's with z's, we get this. So notice the definition of cosine of z and the definition of cosh of z are very similar. In fact, cosine of z is cosh of iz, and cosh of z is cosine of iz. So you see this beautiful connection now between cosine and hyperbolic cosine that only becomes apparent once we get into the complex numbers. Now, last of all, what about sine of z? Well, it turns out this is the definition of sine of z. It's e to the iz minus e to the negative iz over 2i. But where does this come from? Well, essentially what you do is instead of doing e to the iz plus e to the minus iz, you do e to the iz minus e to the minus iz. So you take this formula and you subtract this formula, and that formula for sine pops out. And once you have that formula for sine, you can just plug in I to find sine of I, and it turns out you can check it's a pure imaginary number. It's not going to be a real number. Now, if you love this math as much as I do, then stay tuned to my channel because I have plenty more of this kind of beautiful math coming out.